Section 16.6, the speed of sound. So it turns out that sound travels through gases, liquids, and solids at considerably different speeds. This table 16.1 shows a number of different ones, right? We're most familiar with gases, specifically air at 20 degrees Celsius. This is going to be our standard speed of sound, 343 meters per second. So this is a good one to note because on homework problems, you may need to look up the speed of sound. If it doesn't mention any details about the temperature or the environment, you can assume that you're in normal air at 20 degrees Celsius. But notice the speed of sound is much faster for, say, helium. That's why you can get some really interesting effects if you've ever sucked on a helium balloon, right? People's voices suddenly get higher because the air is so much faster. But even more so than these, look at how much faster the speed of sound is for liquids and through solids. So there's hugely dramatic differences here. Now, how do we go about calculating these numbers if we wanted to calculate it, right? If it wasn't something that we were looking up in a table. Well, if we want to calculate the speed of sound for a gas, it's going to depend on when those molecules are able to collide with each other. Because if they're just separate next to each other, then the disturbance won't pass. They could just oscillate without interacting. So they need to be colliding so that these condensations and rarefactions of a sound wave can move from place to place. So it turns out for an ideal gas, the speed of sound is given by this equation. V is equal to the square root of gamma kT divided by m. Right, where here K is our Boltzmann constant again, 1.38 times 10 to the minus 23 joules per Kelvin. Gamma is what we saw back in the last chapter. And depending on the type of gas, if it's monatomic, gamma will be 5/3. If it's diatomic, it'll be 7/5. It's the sort of thing that will have to be mentioned in the problem. And we could compare this with the equation we got for the RMS speed of gas molecules. So if you remember, we saw the RMS speed, which is sort of like the average speed of gas molecules, is the square root of 3 kT over m. So it's almost the same, except instead of the gamma, there's a 3. Since gamma is always less than 3, that tells us that the RMS speed of the gas molecules is higher than the speed of a wave, the sound wave passing through a gas, right? So that makes sense because we need collisions. So it's going to be slower for the sound to move through than the speed of the gas itself. All right, taking these ideas into account, let's look at a conceptual example of lightning, thunder, and a rule of thumb. So there's a rule of thumb for estimating how far away a thunderstorm is. After you see a flash of lightning, count off the seconds until the thunder is heard. Divide the number of seconds by 5. The result gives the approximate distance in miles to the thunderstorm. Why does this rule work? Well, if we think about this, the speed of sound we saw was 343 meters per second. You may remember from an earlier video, the speed of light is 3 times 10 to the 8 meters per second. Speed of light is much, much faster than that of sound. So if we imagine a person who's 1 mile away from the lightning and the thunderstorm, we could figure out how long it would take the speed of the sound to reach her. Right? So we could get that time if we said equal to distance divided by v, where this is just a rearrangement of velocity is equal to distance over time. And so the distance is 1 mile, which is 1.6 times 10 to the 3rd meters. And we'll divide by the speed of sound at 20 degrees Celsius. And it turns out that comes out to about 5 seconds. Now, if we do the same thing with the speed of light, we take this 1,600 meters and we divide by 3 times 10 to the 8th, which is way bigger, you're going to get a very, very tiny answer. It's very close to 0 seconds. So this is why this rule of thumb works. So next time you're in a lightning storm, which may not be until you travel to the south, you have this rule of thumb, and you can know that it comes from the difference between the speed of light and the speed of sound, that the speed of sound is that much slower than the speed of light. Right, now we mentioned the speed of sound in liquids and solids. If you wanted to, you could calculate this as well. For liquids, it's going to depend on the square root of the bulk modulus divided by the density of that liquid. So here are some values of the bulk modulus. This is going back to table 10.3, right? And some densities of common substances. So you have your density there and the bulk modulus, and you could calculate it. Similarly for the solids, it's going to depend on the Young's modulus, which came from our elasticity as well, divided by the density. Taking the square root, that will give you the speed of sound in a solid. And as you look at these values, you can see that these both moduli are very large values. That's part of why the speed of sound is so much greater in a liquid and a solid. The density is also pretty great, right? But not nearly as great as these 10 to the 10 values for the bulk modulus. And this is why they said with trains, you could hear them coming not by just, listening to the air, but by putting your ear next to the rail of the train tracks, because that metal rail is going to transmit the sound of the train coming much faster than the air. So this introduces the speed of sound. Stick around for more sound in the next section.